Yeah, I'd like to echo that. Any feedback would be great to secure. Okay, so we will now shift gears a bit. Time allowing, we may come back to re-examine another type of hybrid modeling, one that combines not system dynamics and agent-based, but agent-based and discrete event modeling for service encounters. But I'm biding my time, and I want to hit on some key things first before we get to that point. There are videos where I will go through that in some detail. So the first thing I'm to hit on is something I emphasized from yesterday. You'll recall that when we ran this model yesterday, and it holds just as well for this model that we've been running here, we noted a certain variability of outcome. I noted yesterday that if you go to a simulation and you scroll down, there's this area where it has to do with replicability. It has to do with randomness, how random numbers are handled, whether every time it's a different random number or whether it's a reproducible sequence every time. And regardless of whether it's a hybrid model or not, we're going to see a certain variance in the outcomes over the course of the simulation. So as I'm running this here, we're going to see a certain prevalence, for example, of diabetes up here, and prevalence of obesity, and that will vary a little bit between runs. I would note, incidentally, the performance of our model has been somewhat adversely affected by the fact that we're computing particularly these physical activity levels. And it's particularly gratuitous because we haven't hitched this up with the other things. But we'll bear with that. We wanted to show the concept. But the point is that for each run of this, we're going to get somewhat different results. And if we're going to try to value, say, one intervention over another, to do so on the basis of a single run, a single so-called realization, would be perilous indeed. Even if we had all the same parameter values and assumptions, there's going to be variability. And potentially that variability will be large. We want some way of developing confidence that when we see differences between, say, an intervention in the baseline or intervention A and intervention B, that difference is not merely a fluke of chance, that it's not merely an accident, that it's something structural, that it's something that reflects the underlying distributions genuinely favoring the intervention over the other. So, ladies and gentlemen, I would like to take this opportunity to show you how we can compare things in a more robust way, not for just a single run of the model, but for multiple runs. Is that okay? Now, I have a hidden agenda in doing this. The hidden agenda is that the explanations that I'll be giving now and the mechanisms we'll be using in this regard will further be used for the calibration, to understand calibration. If I were to take on the task of explaining calibration, much of it would be harder to understand without this first exposure to the basic ideas associated with this next little exercise. I don't have time, regretfully, to build up a calibration exercise all the way from scratch with simple data, etc. So we're going to need to satisfy ourselves, need to tolerate working with a pre-existing model there. But your understanding of that model will be much, much greater having gone through is likely to be significantly greater having gone through this little exercise first. Okay? Because the basic principles carry over from parameter variation experiments to sensitivity experiments. To calibration experiments. Okay. So So are you ready to go? Fortified by the banana bread? Having quaffed the coffee and invigorated? Okay. I'm holding my banana bread in escrow for when I may need it. Okay, so ladies and gentlemen, let's save this model as befits it. You may have to modify something like drag a little thing slightly to do save as, file save as, and let us increment the number, version 1, or you can give it a nice name. Great. Okay. Because it's very common to save successive versions of a model with incrementing numbers like version 1, 2, 3, 4, 5, and it anticipates that by default. It can be a little bit annoying at times. Like, for example, when it was SACS 2015, it turned that into SACS 2016, which was which would be a most welcome product for next year, but it's certainly not the implications. So it was thinking that was a version number, where instead it was a year. So it can be misplaced in quite a few cases, but that's what reason it does it automatically, because of this very healthy habit people have of saving successive versions. So they always have recourse, or so they are very likely to have recourse to the version that was used, say, to send in those results for a paper, or to do this analysis, for a certain report. You have that version, and so it increments it automatically as the name. It's nothing deep. You can always override it and change it. Indeed. Yeah. Right. Indeed. Indeed, I sympathize. Yeah, I do. I've done the same thing. It was version 1. I wanted to give it the next version. Automatically made it version 2, and I'll make it version 3. You skip version 2, right? Yeah. Well, we can put back a bit of feedback to the mothership if you want. Okay, should we go? Okay, so what I'd like to do here is it'll require a little bit of mechanism here up front, wee bit, but we'll be rewarded with the fruits of our activity soon enough. So, ladies and gentlemen, I'd like to introduce you to a new beast. A beast not venomous, helpful. And that beast will be in the analysis data, and it will be called the data set. And this is going to be data set. We're going to drag in 2 such data sets. One for, we'll just do it with one in the interest of time. We'll do it a data set for diabetes case count, diabetes prevalent case count. Dragged into person. Thank you. Oh gosh, you could see how careful you have to be for that. Yes. Thank you very, very much. Okay. Okay. So I'd like to drag in a data set into main, and this will be data set diabetes prevalent case count. What is this data set? This data set is going to hold data from the model. A very common need, well, not the only one, is to hold data over time. So for successive periods of time, what were certain values, say the count of diabetes cases over time. There's other uses for data sets too. For scatter plots, they hold X, Y values. But in this case, it's going to be this diabetes prevalent case count over time. Maybe I'll make that clear. Diabetes prevalent case count over time. Just to make it clear. And you'll notice that when we do this, it does have this checkbox, use time as horizontal value. Okay? Okay? data set diabetes prevalent case count over time. Now, you notice, folks, that there's a name here. We have this selected. So horizontal axis is grayed out. But what is not grayed out is this one, which is the vertical axis value. So this is basically recording over time for successive time points. It's recording some value. So you can think of it as kind of associated with a function of time, some value. Some value is a function of time. Value indexed by time. And what value will this be? Well, you tell me. How could I get the diabetes prevalent case count? Think back 2 days to the final session, I believe, before the Nolian interlude on Wednesday. Okay. I think it was a statistic that we created, population dot, and I think there was a thing called prevalent diabetes case count. Do you see it there? If you do population dot, and then you look through all choices, there's a prevalent diabetes case count. Let me do that again. Population dot, control space. You notice it gives me lots of choices, but if I can use these down arrows, and I can go down and I'll see, oh, prevalent diabetes case count. Do you see that? And I'll do that. Okay, so we're telling this data set to do this, and we want to update it automatically every 1 year, starting at time 0. So this data set will take care of recording the prevalent case count for diabetes over time. Year 0, year 1, year 2, year 3, just like that. We're telling, create this data set and get it to automatically request this value and record it every year. Is that okay? This is a very useful thing. You can use this for graphs. You can use it to output data to a file. Good things, good stuff. We use it to output data to R automatically. So we have a little thing that puts it out, and R will suck it in. We'll suck it into these data sets. We use the data sets to store the requisite data. It figures out, our thing automatically figures out all the data sets in a given folder. You don't have to tell it about it. It roots them out, and it saves them away and exports them to R. Ladies and gentlemen, so we've created this data set, and that's all we need. That's all we need. People comfortable with that? Let's run the model, and let's see that data set. Let's go browse that data set. One of the many virtues that recommends data sets is that they're very visual creatures, unlike the platypus, which operates in murky water. So I learned at the Toronto Zoo last time. And it has location through electrical. Yeah, electrolocation. So here's the data set here, and you'll notice that the data set is characterizing the number. And you'll notice there's actually a nice little graph you can do associated with that. Okay? People comfortable with the data set? Okay? Great. So here's our little data set, and that's what we're going to need. Okay, so the next step, are you ready? Here we go. The next step is to add a new type of experiment. New experiment, and this will be a parameter variation experiment. Okay? Call it parameter variation, that's fine. Maybe we want to call it something else. Maybe we want to call it baseline parameter baseline ensemble. It's going to run it many times. But for the baseline, No changes to assumptions. We're actually not going to use it to vary parameters here. Yeah. Great. Now, in this experiment, we're going to add some mechanism as well. And I will ask for your pardon as we add 4 major structures to it, no less. Okay. The first thing I'd like to do, ladies and gentlemen, is to add a, if you could go to the palette. Go to the palette, and I'd like you to go and, in the palette, I'd like to go to the analysis area, okay? Right, the analysis area. So, analysis area, the palette, and I'd like you to drag in 4 things. The first is more familiar, a histogram data object. Well, maybe you tell me. I want to add a histogram chart. What do I need to do to add a histogram chart? We need a histogram data and a histogram chart. Okay, great. There needs to be not only the histogram chart, but also the histogram data object that will populate that chart. So here's going to be a histogram, and this is going to be a histogram of cumulative costs at time 100. Okay? Histogram of cumulative costs at time 100. Next, ladies and gentlemen, I'm going to add the thing on which this chart will depend. And what is that? A histogram data. This, ladies and gentlemen, will be called histogram data cumulative costs at time 100. They go together. Okay. Okay. Great. So there's a histogram called histogram cumulative costs at time 100, and then there's a histogram data object, cumulative costs at time 100. And let's wire up the histogram to refer to the histogram data object. How do we do that? I'm clicking on the histogram. How do I get it to refer to the histogram data object? Add histogram data, yeah. And this will be cumulative, the title will be cumulative costs at time 100. And what will the so-called histogram be here? Histogram data. Okay. Oh, no. Oh. Histogram data, cumulative costs, time 100. Yeah, the thing I added alongside of it. Okay. Are people comfortable with that? Okay. The next thing that I will show you, so that may be familiar. A little bit like a marsupial to someone who grew up in North America. After all, we have opossums there as well that are marsupial, and therefore they're not entirely foreign to us. But the next thing will be foreign indeed. The next thing will be more like a monotreme. Leathery egg laying. Nursing through patches on its skin. So we're going to add in what's called a histogram 2D object. Now this is unfamiliar indeed. It's not just a single dimension histogram, it's 2-dimensional. It'll be dividing things up into time, into bin. You know, a histogram divides things into bins. We say it bins, it counts the number of things that fall in a given bin, right? In terms of values. A 2D histogram will count the number of things that falls in a certain bin according to time, and then another bin according to the value of interest. In other words, maybe it's the number of people who are diabetic at that time. It'll be counting the number of runs where at this time the number of diabetics fall within this range. That, ladies and gentlemen, is the job of the histogram data object, histogram 2D data object. So let us add that. So a histogram 2D chart I just added. And I'm going to guess what I'm going to need to guess by what it will be accompanied. Histogram 2D data. Histogram 2D data. Okay. Good. You know what? We should be careful though. We should give these better names. This is a histogram 2D diabetes, prevalent diabetes case count. And the other one will be, so histogram, the chart will be histogram 2D prevalent diabetes case count. And the data will be called histogram 2D data prevalent diabetes case count. Are people okay with that? Okay, monitoring. Okay, next, we're a lot of the way done here. We're much of the way done here. Perhaps arguably most of the way done, but about halfway probably. Okay, for this 2D data object, guess to what it will refer, just like the histogram that came before it. To what will this histogram 2D refer? It will refer to the data, to the histogram 2D data. So the title of this will be prevalent diabetes case count. And the histogram here will be what? Histogram 2D data prevalent diabetes case count. So we're adding things in pairs. For the histogram chart, we need a histogram data object. And the histogram chart needs to refer to that histogram data object. Did it not? It did. Similarly, for the histogram 2D, we have a histogram 2D chart, and accompanying is histogram 2D data, and the histogram 2D chart has to refer to the histogram 2D data. Does that make sense? Now, there's some wiring up of these things that we're going to do in terms of the detailed settings, but we'll come to that. I don't want to lose track of the big picture, and I'd like to come back and return to that. Are people okay with what we've seen thus far? Okay, now, what we know is not unfamiliar at a certain level, although we're dealing with monotremes, with these 2D histograms. They haven't really stretched us fully yet. Yes, this idea of a 2D histogram, something which bends in the X and the Y location, is perhaps not an everyday notion for you. But at least you have a point of reference in a histogram. But now I will show you something quite different as well. So, ladies and gentlemen, this will be something that's a significant departure from what we've seen. Ladies and gentlemen, to this point, when we have run experiments, we run the experiment, it brings main into existence, runs it, a main object, runs it along till it finishes, and the experiment is basically done. Is it not? That's sort of the life of the experiment is the word is escaping me, coterminous with the life of main. Main gets created quickly within it, and just before the experiment finishes, main is finished. Right? The experiment runs main how many times there? Just once. Okay. Now that bond will be broken. That shackle will be loosened. Now, ladies and gentlemen, this baseline ensemble in a way that befits its name, will in fact be able to run the model many times. So if we go to baseline ensemble, we click on that again, and we click on freeform, we could set the number of runs, say, to be 50 runs with the same, perhaps by, for now, the same basic parameter values. We're going to run this thing 50 times. But how, ladies and gentlemen, how for each of those runs will we display the results? After all, we had diverse outputs, manifold outputs that captured graphs of interest in main. We had some anyway. But I was thinking of the GDM model, but here we had some. But those are in main. This is going to run main many, many times, 50 times. And we're not going to have the luxury of seeing those. Now, that's a plus because it means it doesn't have to do all the work to show those to us. And there's often a lot of work being done by any logic to make that visualization show in front of us. We're not going to need it to do that work. So it's going to be able to do it faster, actually, run the model faster, a notable advantage. But we do still want some way of getting access to what this data is. And thus far, ladies and gentlemen, what we've added here, this histogram object, histogram data object, histogram 2D data object, they stand ready to serve as vessels for capturing this data. But they don't know how to get the data out of main. It's going to be running main again and again and again and again. And each time it runs main, there's data produced, is there not? Data till time 100. And somehow, this parameter variation experiment needs to extract that data, suck it out of main, and display it so that we can see it, so that we can get a summary over many runs. Does that make sense? Now, it turns out we're going to come back. It's exactly this issue. This is a distinct overlap with calibration. This is basically where the two are extraordinarily similar, because calibration is also going to run this model many times. The fact that we're doing this now by hand will lend us significant insight into what's going on in calibration. Let us peer through and pierce the confusion that often accompanies it. Okay, so what stands before us is we need here it to actually salvage this data from main every time it's run to completion. Suck that data out, suck it out and display it. Suck it out and present it to us. And then we need to run it again. It'll run it again. And again, guess what will happen at its end? Does anyone want to express it? It'll suck the data out and display it to it. Just like that. Again and again and again and again. Okay? So this thing will be running the model many, many, many times, and each time at its end, you know what will happen. It'll suck that out and display it. Okay? And it will be accumulating statistics. Statistics summarized, no less, in a histogram and a histogram 2D. Histogram 2D will show over time diverse trajectories from different runs of the model. Show how many of them went up here versus down here, and that sort of thing. The histogram will instead summarize at the final time of the model. In our case, do at the final time, at time 100, it'll show the number of cumulative costs. So I'm showing both ways of doing that. In short, though, to be able to display those, what does it need to do for main at the end of each run? You know it. It needs to extract it, right? It sucks it up. And so, let us now figure out exactly how it does that. Okay? Okay. So, ladies and gentlemen, let's go to the parameter variation experiment, and let's go to an area that may be forbidding by its name. It's called here. Well, first let's go to model time, and let's run it to time 100. That's great. But we will go down to Java Actions. And now we'll see something that may be confusing. See something that may even seem forbidding. We'll see little things here. And guess what needs to go into some of these? Can you dare speak its name? What needs to go into these boxes? Code. Indeed. 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 So, okay. So, believe me, this won't be too bad. Okay. So, ladies and gentlemen, understanding this will be very helpful for understanding calibration. So, initial experiment setup. When we first run this experiment, we want to, in case the user has just run a previous one, and now they want to run this one again, we want to clear out any data structures. We want to get rid of anything that's been stored up in the histograms or histogram 2D. So we need to reset them. So ladies and gentlemen, watch this. Initial experiment setup, I need to zero out those data structures. So they're ready to take data for the first time from just this experiment run. After all, that previous one may have been done with different parameters. We don't want any of that data. Ready? Are you ready? Histogram data, cumulative costs at time 100 dot reset. Histogram 2D data, prevalent 2D data prevalent diabetes case count dot reset. That's what I need. That's the Java code. It seems not to be bringing people to their knees. So this is resetting these things. It's just saying clear out any data from here from before. The housekeeping. Okay? Okay. So that's great. Now, you'll be happy to note that in this case, there's only one other thing that we have to put in here. And this one will involve a little bit more of a stretch for you. But compared to what you've been through, compared to your heroic performance yesterday, absolutely heroic. I'm so impressed. This next thing will be, I was going to say small potatoes, but maybe there's a Australian native subterranean vegetable that. Okay, nothing comes. Peanuts? Okay. Okay, so after simulation run, this is what I want to do. What do we need to do after each simulation run? After main has been run, that's what it means by simulation. Main has been run here. What do we have to do? We have to get the data out of it. Do we not? Okay, so let's start with the more familiar one. Let's start with the marsupial. Histogram data, cumulative costs at time 100. What do we have to do? So this is the histogram data. Okay, refer to its name. What do we have to do to it? We have to, this is the guy living in the experiment. Living in the experiment. We want it to hold the values from main. So what do we have to do? Suppose we had a value. What would we do to it? What would we do with this? We would add it to it. Dot add. And there's going to be some value. Now, which value? Which value do we add? The value from main. Okay, now, I'd like to introduce you to an awkward name. An awkward name indeed. And I'm sorry to have to tell you this, but the place you actually refer to name is indicated here. It's called root. Okay? Perhaps the subterranean tuber would be appropriate. So root dot, and where are we going to get, if this is referring to main, root, where are we going to get the cumulative costs from? This has already run it to time 100, so we don't have to worry about getting it at a past time. It's at the right time. How do we get the cumulative costs? Root dot cumulative costs. So we're extracting this from main, and we're putting it into this data set, histogram data. Does that make sense? So we're rescuing it from main, because main is going to disappear in a moment. Main is going to vamoosh. It's going to go back and run main again, and again, and again. And every time, we have to rescue the relevant data from main and add it to our data set, our histogram. Does that make sense? Okay, who needs Delanian help? Okay.
Because there are a bunch of those boxes, and it's not immediately.
I'll come back to that. Yeah, come back to that. Okay, so histogram data, cumulative cost time 100. We will add to this. This is just a histogram we set up, right, in the experiment. We're just going to add to that histogram the cumulative cost from main. We're rescuing that thing from main, and we're going to add it to our histogram. Do you remember we added a histogram a few days ago? Remember we had a histogram for a person? We added things into it. We added just this sort of way. That's nothing mysterious. What's different is that we're rescuing it from main, because main life is limited. Okay, the next thing. So we're almost done. We're almost done here, folks. Watch this. Histogram 2D data. And what do you think we're going to do for it? Add. Good. And look at this. What can you add to the histogram 2D data object? You can add a whole data set. A whole data set. Now, where could we find a data set of prevalent diabetes case counts? Yeah, we already added one. Remember? At the beginning of this session, we added one. So how do we refer to main? Root dot data set diabetes prevalent case count over time. Okay. Ladies and gentlemen, that's it. We may tweak things, but that's the basic gist of it. Make sure it compiles. Make sure it's happy. And, okay, who needs help? Who needs help? Okay, let's run this thing. Can we run it? Let's go run it and see what weird things happen. I think some weird things will happen because we haven't tweaked parameters. Now watch this. It's doing this. Oh, look, it's actually running something. Do you see this? It's actually running on 2 cores at once. This is basically my computer can run it on 2 cores here. And so it's actually running it simultaneously 2 different times. Why is it running at 2 different times? Well, that's the whole point, right? We want to look at variation each time we run it. So it's running it along. Hasn't finished quite yet. Those things we added, those stocks and flows for physical activity, are slowing it down. Okay, fine. Come on. It's just about done. And what will happen when it's done? Boom. Look at that. What do you see there? What do you see there? Okay. What you see there is now this bottom one, though, doesn't have anything on it. Why not? What could be off about the bottom one? Take a look at the values that are shown. Are those values the values you'd likely see for prevalent case counts? Between 0 and 1? No, they are not. They are not. So, ladies and gentlemen, the bottom one needs to be refined. The top one, on the other hand, seems to be okay. You'll notice that this is running along. We'll just make sure the top one looks hunky-dory, and then we'll fix up the bottom one with some settings. I think that should all be, that's required. Okay. It looks like there's very little variation at the cost at time 100. Despite all that variability, when injuries occur, what have you, it's all pretty consistent, it looks like. Okay. Okay. Let's go take a look at this. Yeah, it looks like those costs are pretty standard. Okay. I'm just gonna right-click on this, copy all. Let's go copy that. Let's paste it into a. Surprised there's not a little bit of variation here. I'm gonna paste this into Excel. I right-clicked on it, said copy all. So here it is. The minimum is this. The maximum. Oh, look at that. It's basically there's zero. Jeff would have a more colloquial way to say it, but there's zero variability. Local car. So there seems to be actually zero variability here. Let's go look at the bottom one. Do copy all for that. And then let's go paste that somewhere and go see what's going on there. Oh gosh, this is horrible. It used to be much better at displaying those things. Okay. Okay. In any case, we won't dwell on that right now. So let's go down, and it looks like each time it's getting the same value. That's an unexpected thing. I'm going to go figure out why. Okay, so here's the ensemble. Let's go look at randomness. Ah, there we go, folks. The fox has shown its tail. Huli Jojo Bweba. Okay, so we had it. So what it tells is that when I looked at it, randomness was fixed seed. Why was that giving me those results? Why do I say the fox has shown its tail? Why does this fixed seed immediately tell me what the problem is? Same set of random numbers. It's running exactly the same thing every time. So we need to change it to random seed. Okay, now let's see what we got. We still haven't fixed the bottom one. Let's just see if the top exhibits variability. Okay, so here we go. 2 runs are coming along. It turns out that running things in parameter variation experiments is typically, when you have a model with lots of visualization, this can be very much faster. It may shave 40% off the time. Yeah, question. The model got full of that means you have 4 cores at your disposal. In other words, your computer, your processor has 4 different units it can use to simultaneously simulate the model. So it's running it 4 in parallel at the same time. So instead of just waiting for 1 at a time, you can actually run 4 at a time. And that allows you to do it much quicker. My computer actually has 4 cores, but I only gave 2 of them for Windows to work with. 2 of them are reserved for well, yeah, all 4 are for Linux. So that's why. If other computers, if anyone has an oct core, you'll see 8 bars moving in an impressive demonstration of computational.
What if you had 1 bar?
Well, yeah, it's trying to run many things. Okay, so let's talk about that as a practical matter. Suppose you're seeing your memory go into red down here in the lower right. This is an indication of memory, and memory issues if it's red. And so one thing you can do, this is important, if you're encountering memory issues, you can scroll up here and give it more memory in this maximum available memory. And that will make it less likely that it'll get in a memory starved condition. So you can devote it more, and often that can be done in a fairly lightweight way, and it will take advantage of it. So what we're seeing here is, folks, there's some variability. We haven't yet gotten enough samples. We've only gotten 5 samples thus far. We'll soon have 2 more. But fundamentally, we're seeing some variability in cost, but it's pretty minor. Small potatoes, small peanuts. Yeah. Okay, now we're going to go down and we're going to fix the bottom thing. Okay, here we go. We're getting a little bit of a peek at a sampling from a distribution here. Okay. Okay, next, let's go down and let's fix up that 2D histogram. And then, within our belt, we'll be ready to take on the rigors of calibration. Okay, so, ladies and gentlemen, let's go down and fix up that 2D histogram, which thus far has been underperforming. Okay, so here we go. Here's our 2D histogram. Let's go take a look at what's going on. Go to the histogram 2D data object, and you will see that it has an X value range and a Y value range. Once again, the fox has shown its tail. What's the matter there? What is this data? What is this 2D data histogram just supposed to display? Prevalent case counts of diabetes. Yeah, over time. So the X should be time, so that should go from 0 to 100. We might break it into 50 categories, maybe 20. Yeah, you could do it that. It's not that prohibitive. But the Y value range is out of whack. We were seeing things, I think, up to, 100 or 200. So I'll just say up to 200, 20 intervals in the. So this is the number of bins in the Y direction, number of bins in the X direction. So we'll do X, 50 bins from 0 to 100, Y, 20 bins from 0 to 200. Ladies and gentlemen, let us run it. Does anyone want this on the screen more? So again, X, so I'm looking at the histogram 2D prevalent diabetes case count. This is the data, the object to hold the data. And we have X going from 0 to 100 with 50 intervals, Y going from 0 to 200 with 20 intervals. Okay? Can we run it? Let's go run it. Run. Okay? You notice that the scales are different now. We have X scale here corresponding to time from 0 to 100 and the other from 0 to 200. So let me ask this while this is running. Why not display each trajectory exactly or close to exactly? Have it be very precisely shown. Why not just show that? Why do a histogram? Well, the answer is we want to see actually there's going to be certain bins that are occupied more. If we showed each trajectory atop each other, it's hard to see the high density regions. There's a lot of things atop each other. It can look like a hairball. And this at least starts to show us which regions are sort of more in common and which are less in common here. You notice this is rising. I should have evidently given it more for the later times there. But we'll just let it run. So what do you think those represent? These are places where a lot of runs. In this case, it's just 2 out of 2. It's running some more right now. But these are places where there's been high density. And then there's some things on the side where it's, fewer runs have ventured. So here we go. And what we see is, ladies and gentlemen, a mark of of structure and yet randomness around that structure. It's not totally deterministic, to be sure. There's some variability, but there's a lot of regularity, a lot of structure, a lot of order to it. Order and disorder, each in their measure. Sometimes it can, but here it's not. It depends on the number of cores that you have. This gentleman back in the back there, it might work for him because he has 4 cores and each of them needs separate memory. In case with just 2, I'm not seeing this turn red, so it's probably not a sign it's memory starved. In which case, increasing the amount of memory, I would say, would offer marginal benefit. It's just if it's memory starved, if it starts being red, that would be a sign that, yeah, increasing memory might spare you some time. Okay, ladies and gentlemen, so we've seen a 2D histogram here, and we've seen a histogram on the top. On the top lies the marsupial, a familiar artifact from previous runs, yet used in a novel way. Here used to summarize results across many particular realizations of the model, running the model many times again. Just like that. The bottom represents our monotremes, a more novel structure, less familiar, a 2D histogram, but one which gives us quite a bit of interesting information about variability in the context of still some order. So you'll see, yes, there's quite a bit of variability, but there's a tremendous amount of similarity between the results in terms of the number of the prevalent diabetes case count over time. Despite the randomness, there's a lot of order there. Okay, so any questions related to that? I'm going to come back to the Nolian request in a bit. Are people comfortable with this? I know. Yeah. Sorry, here? Or this is just a histogram, so. Oh, the one below. Yeah. Oh, okay. Okay. What I'm trying to get at is why is it doing that when it's really just a number of, why are the simulations changing so much? Why is it changing the histograms, why is such a wide variability? You mean up at the top or at the bottom? Well, the bottom summary of the histogram, isn't it like being simulated? Well, okay, so let's talk about that a bit. So it's a great point for me to expand on this a little bit. So this bottom one, it's what we call a 2D histogram. So at a given point here, let's say this time 10, if we were to cut through this, there would be a histogram in terms of the number of diabetes case counts across the 13 or 14 different runs that have been made. So there'd be some histogram here that goes kind of like that, and that's what this is showing. Time 20, there's a histogram here, and it sort of goes down like that. There's actually time intervals between 10 and, I guess they divided this into units of 2. I think it was 50 for the 100. So it'd be for this sort of between 10 and times 10 and 12. If I summarize the different runs, a certain number during that time interval fell in here, a certain number fell in here, and that's why this had more things falling in it, so it's darker. This one had fewer, therefore it's lighter. But if we were to cut it and look at it from the side, we'd see a histogram sort of that was higher here and then went down here and then went to 0 up here and it's 0 down here. So that's what this represents. And it's just summarizing across different runs. Each run is adding a sample to that histogram for that time period. Well, so yeah, I mean, not what this is showing doesn't directly tell us anything about model correctness. What this is showing is the degree of variability in model runs from run to run to run, just because of the simple stochastics of the situation. So we have a run here. We have a model which exhibits stochastics, and maybe I should have emphasized this earlier. So here's our model. Where are the stochastics in this model? Where is there kind of uncertainty over time? Can anyone tell me? Where are there dice being rolled, so to speak? The initial state. Remember, it drew from a distribution. Another place is where? Yeah, these transitions, they were based on, they were rates, hazard rates, and it was essentially drawing from a distribution as to when you'd go across there or when you'd go across here. These transitions, in fact, this transition here, these had some stochastics associated with it. And those stochastics at the individual level, the vagaries of when one person happened to develop overweight or to become obese or to undergo injury and become disabled, those were contributing to some variability in the costs at a given time, say at time 100, as shown by that top histogram here, and some variability in the prevalent case counts of individuals with diabetes, the number of people. Some runs, by the luck of the draw, had fewer people with diabetes by time 20, say. Some runs had more people with diabetes by time 20. And as a result, and this is showing you that variability from the model. Now, as far as kind of correctness of the model, part of what this alerts us to, I mean, this is relevant for developing confidence in the model in the sense that if we are seeing a range of variability here that is circumscribed and is far, and we're seeing empirical data from the world that falls nowhere near the ranges elicited from this model, that would lead us to question, to what degree is this model reflective of the situation out there. On the other hand, perhaps empirical data we have from the world to which we would compare a model like this for a given cohort or a intervention group in an RCT or what have you. For that sort of situation, if we were to compare the model results against empirical data, we have to recognize the model has some variability. So if we got data from this RCT which fell in this bin here, we'd recognize, well, that's well within the 95% empirical fractiles of the model, within the sort of appropriate quantiles of the model for us to feel comfortable that the model may still be representative of the situation. On the other hand, if our empirical data fell out down here, or fell up here, it'll be a sign, okay, the model doesn't seem to be putting out results, despite some variability being elicited from run to run to run as to how many people are diabetic at this time. The model's variability puts it at a far tighter level than would be used to explain this empirical data. So it has something to do with plausibility of the model, but this is just quantifying how variable our results are. And for some models, and for some situations with those models, some parameter values, you'll find huge variability for this region and then it will become more narrow, or vice versa. There'll be certain regions where it's wide and certain regions it's small. And it's useful to look at that, to see how much variability there is. Dr. McDonald, from this very podium 3 days ago, noted this distinction between the empirical, the actual, and the real world as characterized by the certain philosophical tradition of critical realism. And there's this distinction between, there's this notion that, okay, I think it's related to, as best I understand it, far from being a philosopher, what we observe in the world, we could think of as being one realization of a process that has some variability. And as such, we don't necessarily expect the model to precisely always match the results, but we would like to have some confidence that the model's degree of variability would allow for the empirical data that we observe from the model from the world to actually be compatible with that data from the world. I don't know if what I'm saying is meaningful.
No, I suppose how I'm trying to interpret the prevalence of diabetes count.
Yeah.
And as I understand it, this actually represents a summary of the model being done numerous times.
That's right. Yeah, that's exactly right. Yeah.
And so, if we run it once, we might get 20. If we run it twice, we might get 25.
Yep, that's exactly right. The second time we might get 25. The third time we might get 15. Yeah, that's right. Yep. Yes.
Do we end up getting a situation where it's plateaued? Because that's what mine is like. It's plateaued at the end.
Sure.
So what does that mean? When you actually, it means that how do we interpret that?
Okay.
The first time it comes, and we get 25, the second time 30, it's about, does it mean that there's a problem with your model because it's not actually predicting the number of prevalent stages you have?
Okay, so I think, so I may be off, but I think that the issue could be, and I'm going to modify my particular display here so that it actually has a larger vertical axis. Did you do yours vertical axis from 0 to 200, or you did? Okay. Okay. So I don't know what's going on, but I'm going to make it very large. By the way, this is with the model with budding, and I'm going to run this thing, and we're going to see. And probably I should have gone and made this into a larger number. I'll make it into 75 different intervals there. Okay, fine. Let's kill this guy off. Okay, and run it. Boom. Here we go. So I'm running this thing. Boom. Now this lower graph, I think you're seeing this plateauing on the lower graph. So this lower graph, to be clear about what the lower graph depicts, the lower graph depicts over time, right, the number of people in the model who are diabetic. And the fact that this curve is going up and plateauing in this case is a familiar feature of a complex system that's reaching some equilibrium in the model. It's not something terribly deep about model correctness. It's an aspect of model dynamics that's very frequent in complex systems. Now, interestingly, I'm not seeing the plateauing right now. But if I ran the model long enough, I probably would. If I ran it for 500, I'd probably see a plateau at some level. But that's not that's a familiar feature of a model. You see this all in kind of complex systems that they'll sometimes go to an equilibrium point where things aren't changing that much. It's a stable situation. When you have a negative feedback, a balancing feedback, you see this sort of behavior. And I don't see that as an aspect of model correctness so much as a feature of its time behavior that's shared between all the realizations, between all the runs of the model. So the fact that it plateaus or not is a reflection of how the dynamics of a given run, does it continue to rise ad nauseum or does it plateau? And I would venture, and I probably should have done this more artfully here, but if I were to run this out for a much longer time, what I would see is probably exactly that. It's gonna plateau at so I'll make it 100 stop time, let's say, and I'll make this guy be out to 500 at the cost of make it take a lot longer. 500, yeah. Yep. Yeah, that's right. That's right. Yeah.
Yeah, so the longer we run it, the more diabetes we're going to have.
That's right. Yeah. Okay. So people comfortable with that? Now, when is lunch delivered? 15 minutes. Okay. So what I'd like to do to then talk, I'd like to open up so that was our